Hello everyone, my name is Shambhavi. Hope you all are doing well. So, in the previous video, we had studied about the goodness of fit test, right? So we had studied that in this particular type of hypothesis test, what you do, you determine that whether the data or which you call as fit is a particular distribution or not, right? This is what you do. Now, the null and the alternate hypothesis for this test may be written in sentences or may be stated as equations or the inequalities, right? The test statistics for a goodness of fit test which we have here is sigma k, and after that we have in the bracket O minus E to the whole square divided by E. What's the value for O that we are having? What is that actually? How to find it out? So value for O is actually the observed value of the data, right? What's the value for E? So the value for E is the expected value which is from the theory. And what's the value for K which we are having? So that's the number of different data sets or the categories. So the observed values are the data values and the expected values are the values which you would expect to get if the null hypothesis were true. So basically there are n terms of the form, that is O minus E to the whole square divided by E. Now we have some more things in this particular interval as well, so I would just begin with that. So the degrees of freedom, G-D-E-G-R-E-E-S, okay, the degrees of freedom are, what's the value for the degrees of freedom? So that is df is equal to number, okay, I will just simply write number of categories subtracted by 1. So this is what the value for df is. It's the number of categories minus 1. Right, so hope I am clear with this particular thing first of all to you. Next, what I'm having, next I am having that the goodness which we have for the fit, right? So the goodness of fit test is almost always right-tailed. The goodness of fit test which we have is almost right-tailed. As I have already mentioned out this thing previously as well, that what are the goodness of fit test we are having, that's almost always onto the right hand side only. That's always right-tailed, right? Next we have that if the observed values and the, let me just go down right here. So if the observed values and the corresponding expected values are not close, now if basically the observed values which we have founded and the corresponding expected values, if both of them are not close to each other, then basically what we say, then the test is statistic, here go the statistic. If the observed values and the corresponding expected values are not close to each other, then what we say, then the test statistic, okay, then the test statistics can get very large, and will be way out in the right tail of the let me just come down right here. So we can see that if the observed values and the corresponding expected values are not close to each other, then the test statistic can get very large and will be way out in the right tail of the test which we are talking about, and that's the chi-square curve. And here is goes that particular curve. Right, so basically what we studied right here, what we meant from this, one second, let me take on the cursor onto hand, right here it goes. So we had seen that the goodness of fit test is almost always right-tailed. Right, if the observed values and the corresponding expected values are not close to each other, then basically what happens, then the test statistics can get very large and will be way out in the right tail of the chi-square curve, right? This is what actually happens. Now here I have a note to be written out. I will just go on like this note, and that is that the expected value, the note is that the expected value for each cells, let me just come down. It goes, okay, one second, run, let me remove out this number which are written, fine. The expected value for each cell uh, needs to be at least 5 in order, in order to use the test, right? So here we have out a note that the expected value for each cells need to be at least 5 in order to use out that test. So let's say I just want to use out that particular test. So in that case, it shall be like the expected value for each cell which we are having, that shall be at least 5. Okay, this is the one of the condition which applies out, that it shall be 5. Then only we will be able to use out that test. Wait, I'll be giving you now a quick revision for what are the things we have studied from the starting in this particular distribution. So we had studied about, first of all, the notation, that puts a notation for the chi-square distribution, that's x square approximately to x square df. Right, what's our df? Df value is equal to n minus 1. What is our df known as? So it's the degree of freedom which depends on how chi-square is being used. Then we have that for x square distribution, the population mean is mu, that's equal to df, right? And the population standard deviation is sigma, that's equal to under root of 2 point, that's 2 multiplication df. The random variable which we have, so random variable is shown as x square but may be an uppercase. The random variable for the chi-square distribution with k degrees of freedom is the sum of k independent squared standard normal variables, right? This is how we just use, and this is how we denote x squared is equal to z1 square plus z2 square plus up till zk squared, okay? Now, what we have the facts regarding the chi-square distribution, so that is that the curve is non-symmetrical and is skewed towards the right. Next, there is a different chi-square curve for each of the df. So as I had shown you in the graphs as well, that when I have taken the degree of freedom as 2, so the graph is different. When I have taken the value for df is equal to 24, so in that case as well the graph is different. So it proves that out, that as soon as the values or the degrees of freedom differs, that your graph will as well differ out in those cases. Okay, the test statistics for any test is always greater than or equal to 0. So test statistic which we have for any test is always greater than or equal to 0. When the value for df is greater than 90, so in that case, the chi-square curve approx the normal for like we have x belongs to x square 1000. So in that case, the mean is mu is equal to df is equal to 1000. Standard deviation is equal to sigma is equal to under root of 2.1000, and that's equal to, it's not point, that's actually multiplication. Okay, make sure to remember that out. Above we have studied out the formula as well. Where is that? Right here we had seen sigma is equal to under root of 2 multiplication df, right? In the same way, right downside as well, we are having the same thing. Now, therefore, the value for x we have approximately equal to n, and that's 1000,44.7. Okay, and that is approximately. The mean, that's mu, which is located just to the right of the peak. As I told you that the mean which we have here is whatever the peak we are having for that particular graph, it's just located to the right hand side of that particular peak. Right, now what's the goodness of fit test? So in this particular type of hypothesis test, what you do, you determine that whether the data, that's the fit, we call it as data or a fit, is a particular distribution or not. Right, this is what we define out here. Then we are having that the null and the alternate hypothesis for the test may be written in the sentences or may be stated as equations or inequalities, right? So the test statistics for a goodness of fit test, the formula which we have seen was sigma k. We have O minus E whole to the square divided by E. What's the value for O? So that's the observed values. That means the data. What's the E? E is basically the expected values. That is from the theory. What's the K? So K is the number of different data sets or different categories, right? So the observed values are the data values and the expected values which you would expect to get if a null hypothesis were true. So expected values are the values which you would expect to get if the null hypothesis was true. There are total n terms of the form that's of this particular form, that is O minus E whole to the square divided by E. What's the degrees of freedom that we are having? So that is df is equal to number of categories minus 1. The goodness of fit test is almost always right-tailed, right? It is observed values and the corresponding expected values is not close to each other. Then the test statistic can get very large and will be way out in the right side tail of the square curve. Note that the expected value for each cell needs to be at least 5 in order to use out that test. Right, hope I am very much clear with this particular thing regarding the quick summary whichever I have mentioned up here regarding all the things. Right, we'll be discussing about some more topics in the further video. So this is all for this video. Till then, thank you and take care.